Whoa, what's up, Doom? Sorry. Been locked in a little bit. How you doing, dude? I'm doing good. It's been busy time, but enjoying myself, so can't complain too much. Hope all is well for you too. Ah! Damn it. Fuck. Alright, we back.
after however many collisions, and that's kind of rare. If you have more collisions, you'll get more Higgs to improve your statistics on what the hell the Higgs is.
Yeah, because we want to know.
But then there could be a reaction that's even rarer to manifest than the Higgs.
Yes.
And if your sample wasn't large enough, you would just never go there.
Yes, you wouldn't see it. If you just made one thing, one particle, you know, whatever it is, the Higgs prime, whatever. If you made one of those, then you wouldn't see it if you made one of them.
Sounds like
you need to make hundreds.
Superhero nemesis. I'm Higgs prime.
Yeah.
You know, I've come to destroy.
And by the way, and we do look for those things. The Z prime, the Z boson, we look for the Z prime because they can be signatures of extra dimensions in the universe, by the way. So we look for this stuff. But the point is that if something is very, very rare, then you won't really see it. If you just make one or two of them, you need to make hundreds or thousands or whatever it is to see them.
Yeah, it's like how many people have to live in a city before you stumble on someone who's 7 feet tall?
Yeah,
that's
so statistics.
Statistically, you need possibly millions.
Yeah. So the upgrades are the upgrades that we can do, and you have to upgrade the detectors, the cameras that we use, as well as the machine.
Okay, so you kept the same hole in the ground.
Yeah, because we don't want to dig another one of those, or change all the magnets around, which are very expensive.
Does that hole go through more than one country, or is it all contained in Switzerland?
It's France and Switzerland.
Wow, okay.
Yeah, most of it's in France, actually.
Oh, didn't know that.
Only a little bit of it's in Switzerland.
Okay.
So that's one thing. And the other thing is, this Higgs that we've discovered, the question still remains, is it the simplest one, the standard model Higgs? Or is it something more complicated? How does it behave? So the analogy in planetary science would be, we discovered a moon. And so you go, great. Then you would like to know about the moon. You don't want to just say, we've discovered this moon, it's a dot. That's fine. As you said, they're interesting.
You want to characterize it in whatever way you can.
For that, you need a lot of them to observe. Mm-hmm. So it's exciting, and it's challenging because I think for the first time, it's probably true to say in particle physics, we don't know if there's anything else just around the corner, which is bad, but it's also good. I suppose it's just science. I mean, ultimately, it's neither bad nor good. It's the way nature is.
That's what triggers whatever next round of physics is complete.
Yeah.
You get those people that show up and say there's nothing left in physics to discover.
Well, they
show up every few decades.
So utterly wrong that they're not even worth considering. I mean, there's tremendous progress being made. It's such an exciting time in fundamental physics at the moment. Not particle physics, not only particle physics, but we said gravitational astronomy, the exploration of the force of gravity, black holes, quantum information, which is related to quantum computing and all sorts of all that stuff is to me utterly fascinating. There's some really interesting stuff. I read some stuff the other day which I don't fully understand actually. Some of the progress in string theory, it's interesting because, just as an aside, it's linking, it seems to me, it's linking one of the great mysteries, which is the so-called cosmological constant. So the fact that we observe that the universe is accelerating in its expansion.
And Nobel Prize has been given for the observation, not for the understanding. Yes.
Yeah. There's a friend of mine who, by the way, didn't believe he didn't believe it when he saw it because it wasn't in the air. This idea, he was looking at light from supernova.
Right.
Supernova.
In fact, I'm on a paper with Brian Schmidt.
Yeah.
I'm like very minor author. You have to scroll down, and then my name's
in the supernova date. Yeah.
But it was analysis of high redshift supernovae.
Yeah.
And I totally enjoyed that work. But he obviously went on and made an entire sort of branch of his career on it.
So there's this remarkable idea which comes from that, which is in Einstein's theory, this idea that you can have a kind of energy in the universe, let's say, or a thing, whatever it is, because we don't know what it is, but something that makes the universe, the rate that space stretches, increase, which is so that's there and it's observed. It's one of the great mysteries because I think it's the smallest number in all of physics by, what is it? It's something like a 10 to the power minus 122 or something in appropriate units, right? Which is an absolutely ridiculously so it's a tiny thing that's causing this rate of expansion, but it's not zero. And so the question becomes, why is it tiny?
Why is it tiny and not zero?
Yeah, yeah,
Right,
and so because if it were even slightly bigger, we wouldn't be here. So the universe would have been blown apart. So it seems very unusual. But I saw the other week, or the other day actually, that there's some research that's linking that in the framework of a string theory or M theory to dark matter. There's a kind of an idea that if you fix that, you get a prediction out that there should be dark matter, but it turns out it's to do with extra dimensions and gravitons in extra dimensions and things. So it's quite interesting. So I think there are some very interesting areas of string theory where progress is being made quite remarkable.
Do string theorists need a fuller or better inventory of particles? So, for example, are we still looking for a graviton? Are we still looking for, you shake a stick and there's a physicist proposing a hypothetical particle to explain dark matter, to explain.
Wouldn't it be cool if the dark matter were related to gravitons, which is this is not my field. I only heard of it the other day, but it sounded interesting. But it just shows you that so to go back to LHC, we have the Higgs particle, as you said. We had expected, I would say most particle physicists expected there would be other particles discovered. There's a particular
in
theory.
that same experiment.
Yeah, at LHC. So there's a particular theory which motivated by string theory a long time ago, called supersymmetry, which is a property of the universe.
It's been around for many decades.
Yeah, and it came initially from either from string theory or from some other physics and got incorporated in. I can't remember historically which way it came, but it essentially predicts that there are double the number of particles that we see, fundamental particles at this energy. So we and they would have been great candidates for dark matter, by the way, which is an astrophysical discovery. So we should say, I suppose, the one sentence description of dark matter is that we see the universe. There's far much more matter in the universe than we can see.
See, I would put it differently.
Yeah.
I would say there's far. It's not dark matter. It's dark gravity.
Well,
you say matter. We don't know what it is.
Well, it's true. So you see it through its gravitational interaction.
So it's dark gravity.
Yeah.
We don't see. Otherwise, you get newspaper headlines say, "Oh, we must abandon our ideas of dark matter." Well, if it's not matter, it's still there. Okay, it's misnamed.
Yes, I see what you mean. I mean, that's a cool newspaper, by the way, that would have a headline like that.
That it goes there at all.
It's usually about a football player, and so I'm on board with that newspaper.
Yeah, I'm just saying, if we don't know what it is, we had no business calling it matter at all.
But, so the thing to say, though,
Call
is
it dark gravity.
The best,
which sounds cool.
So you build models, and it is true that the best model that fits all the data, which is not just the way that that galaxies rotate and collide, and the way that galaxies kind of lens light and all those things, but also the cosmic microwave background radiation, which is the oldest light in the universe, and how that worked, and how the ripples, the sound waves went through the early universe and all that. You put it all together, and it fits if you have a light-ish particle that does not interact with light, but interacts weakly.
So this would be another category of particle in the particle soup.
Yeah. So
that has gravity, but doesn't interact electromagnetically,
yes,
or only very
so
weakly, and so it just is. All right.
Yeah. So that's a model, though. You're right. So that's a model, which is kind of, I would say, the baseline model.
Yeah, it's the assumption. People assume that, and I don't have a problem with it. But if anything happens to that model, it gets shown it can't be true. People say, "Oh, then there is no dark matter." No, there's still dark. It is a measurement in the universe.
Yeah, I understand.
We've just misnamed it.
Yeah, I agree. The measurement is just galaxies spin round too fast.
But too fast. There it is.
Or the way they collide, and so on. There's quite a lot of independent measurements of this thing.
So tell me about graviton. I mean, is that a real particle?
I think most physicists would say that quantum mechanics is the base theory. I think the reason I'm careful is because there are some people who would say general relativity is a thing, space-time is a real thing and all that. But I think that generally most people would say quantum mechanics is underlying it, and that if you have an interaction.
In other words, quantum physics is foundational to the universe in ways that even general relativity would not be.
Yeah, so we could talk about this later, but the idea that space and time, or space-time, emerge from a quantum theory is very fashionable at the moment, partly because of the study of black holes, so we could talk about that. But so given that, then so I should say, just for people who are watching and listening, that so how would we picture the electromagnetic force in particle physics? So we know that if you put light charges together, they repel and so on. So what's happening there? Or if you bring magnets together, right, they repel each other. Everybody knows the North Pole together and they repel. So what's happening in particle physics terms? You picture that as the exchange of a photon. It's a particle of light, goes from one particle to the other, and essentially carries the force. So that's what our particle physicist would picture that force. All forces.
Have we successfully applied that to gravity?
No, so that's the point. But
give me a more resonant no.
The very strong. I suppose I'm trying to find the right word for it. I think that's why I said conviction. It's almost, I don't know of any physicist who would disagree with this
because if you can't fold it into the quantum world, you don't really have a right to start looking for a graviton. Because you're going to say the graviton is the mediating particle.
Yeah, so it's the
in the way the photon is the mediating particle.
So and that's I don't think you'd find anyone who would disagree with that statement.
Okay.
Although I don't think you would. Although it is true to say that because gravity is so weak, so this is the other thing to say, it is tremendously weak compared to the other three forces of nature, of which electromagnetism is
Here's
one.
what I tell people, you've surely done this in class. They say, well, how weak is gravity? Well, I can pick something up off the floor against the wishes of Earth.
Exactly, yeah.
Yeah, the whole Earth is pulling on this ball, and I can just pick it up off and kick it
and
into
you're
the goal.
using electromagnetism. That's what's happening. So your muscles and all that thing. So this is all electromagnetic force, which completely destroys, as you said, the gravitational force.
Right.
But gravity is only additive, so it only adds up in the universe. So it is the dominant force on cosmic distance scales. That's the point about gravity.
Here's a calculation I haven't verified, but it sounded legit. Very verifiable.
Yeah.
I was too lazy. That if you take like the space shuttle in its glory days, and you remove the electrons from 1 cubic centimeter in the nose of the main tank, and take all those electrons and put it at the base of the launch pad, it would not be able to launch. The attraction between the electrons at the base of the launch pad and the net positive charge at the top is enough to prevent it from launching.
Yeah, that's a cool idea. I could see that would be.
Actually, it would
Yeah.
burrow a hole. So
It'd call it, yeah.
It's not a realistic experiment, but to get some sense of the forces involved.
Yeah, that's a really nice way.
Okay, so gravity's weak. That somehow bails you out of this problem?
Well, it just means that we don't have experimental access to them.
Okay.
Because it's so weak.
Whereas we do have experimental access to photons.
Yeah, unless you could potentially have access if there were extra dimensions in the universe that are configured in the right way.
Physicists are always throwing in extra dimensions.
Well,
whenever you need it,
It is interesting, though, that string theory works in 10 dimensions and only 10 dimensions, mathematically. So that's an interesting observation, right? So
I mean, I don't have the background to be an authentic string theory skeptic, but I know physicists who are, and so
I think there are. I mean, it depends. I think it depends what you mean by string theory. I mean, if you go back, a few decades, you talk to Brian Greene, for example, and when he started working in this area,
he's a friend of Star Talk.
Yeah.
He
would have. And his great book, The Elegant Universe, is a beautiful description of string theory. And so I think the idea initially with the hope was that you'd have a theory and you could write it down. It's a theory of everything, and it would predict the universe as we see it.
And then you go home.
And I think that's gone as an idea. But the basic idea of these, I mean, why is it called string theory? It's because particles are not point-like. These strings are like little loops, but that idea, I think, is still at the foundation of most modern theoretical physics in this area. But it's got much more complicated, and it's been much harder. I think the initial idea that you could just predict everything from one number maybe has gone away.
One simple equation on one line.
But there is tremendous progress being made in string theory. So it's not gone away. It's just
Okay.
become more complicated, I would say.
Well, thanks for catching me up on this. At this conference, you're giving a talk on black holes.
Yeah.
And there was some recent announcement, the biggest jet from a black hole ever discovered, ever. When I was asked about it by the press, I simply said, there's always a biggest jet in the universe. And so now this one is that.
It's the A380.
Okay,
The
so
Airbus A380. It's a fantastic aircraft.
did I undersell the significance of this huge jet? So what if it's the biggest one, unless there's some interesting physics that's coming out of it?
The area that I share a PhD student who's working in the area is more theoretical. It's about quantum information, the way that information behaves inside and outside a black hole, what happens to things that fall in. But in terms of the astrophysical work, if you go back, not long ago, we didn't really have any observation of how things behave in the vicinity of black holes. And so I would put it in that box. We've got several observations now. We've got the radio telescope observations from the Event Horizon collaboration that are showing us how the magnetic fields work, for example, around the black hole in the Milky Way. We've got these jets, which are giving you access to the magnetic structure, presumably, in the way that they spin.
Thank you for putting it in that context. Now I can understand. It broadens the astrophysical data set on which we can sharpen our hypotheses for what's going on.
Yeah, because they're hard things to observe.
Yeah.
And of course, you can't observe the interior because it's inside this thing called the Event Horizon. But what you can do, and we are doing, is observe the way that material behaves in the vicinity of them. Or the other remarkable thing we've been able to do in the last few years is watch them collide and see how the ripples in the fabric of the universe come out, and we can detect those ripples. So all these things are allowing us to probe these objects, and it's worth remembering that they were present, they were described, non-spinning ones were described fully by the work that Karl Schwarzschild did in 1916. So months after Einstein had published the theory of general relativity. He didn't know it at the time, but the mathematical description he found, which describes how space and time are distorted in the presence of a star, a non-spinning star, is kind of important. Those fully describe a black hole that isn't spinning.
If I remember correctly, he would die in the First World War. I don't think he made it out of the war.
No, he died in 1916, so it's shortly after. Not in action. He died
was not in action. Okay.
I think he died from diseases that he was on the Russian front.
Okay.
So it was So
it could be war related, but not
it was.
an injury.
I think it was.
Yeah,
You would argue war related.
So we've got more than a century of mathematical foundation for this. Yeah.
And then you go forward to 60s.
With no data. No data.
No, and then so it takes another 50 years, by the way, for someone to work out what it looks like for a spinning one, which is Roy Kerr. It's a famous Kerr solution. But those two solutions are there. They're in Einstein's theory in a sense, and they describe the black hole. But observing them is something that we haven't been able to do till recently. So
and multi-wavelengths as well.
So now we have radio observations, the gravitational wave observations.
I'll be a little kinder to that.
Well, because it's the way. The thing is, as you said right at the start, science is about having ideas, building theories, and so on. But it's really fundamentally about testing those theories.
Yeah.
And so we can talk about these theoretical objects, black holes, but really, and they are rich theoretically. But ultimately, you've got to make observations, and that's where these jets and seeing how material behaves gives you access to the magnetic fields and how the thing's spinning and what it's doing. That's important.
Hey, Star Talk fans, I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version, and you can get that in Spotify, Apple Podcast, and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on Star Talk. Let's talk about your work with the public. You said earlier you share this commitment that Feynman declared, duty to bring science to the public. You not only talk the talk, you walk the walk, and you have spillage everywhere. You've given tours, public tours in Australia, across Europe, and if I remember correctly, you're coming back to the United States next spring?
Yeah.
To give a tour across the country?
Yeah. It's a tour that's been going on for quite a long time. It wasn't meant to really, but we've ended up playing to over 400,000 people across the world with this tour.
Wait.
So,
You're not a musician. You say playing.
Playing.
Get your vocabulary
no,
straight.
I'm rock and roll basically. I always have been that. So, and when we tour,
Playing to 400,000.
we have 5 trucks and 2 tour buses. It's brilliant. So I'm reliving my life as a.
So did I see a version of that when you came to the city?
Yeah, it was very early on. Just after it was just after.
Yeah, you have
COVID,
these
wasn't it?
screens that interlock.
Yeah.
And then the whole stage is.
Yeah, and that was a very early.
This seems quite unique.
Great.
Given things that sort of border on.
Every building could be buried under the depth of the crater. And that was just 50,000 years ago. And as far as we know, not much went extinct then. But oh my gosh, if you were around at that time, that would have been quite the spectacle. The solar system's a shooting gallery. And it's not just stuff hitting us from way long ago. Anytime they show paintings of dinosaurs, there's like a volcano and there's, stuff. No, the dinosaurs were only like 100 million years ago. Earth has been around for 4.5 billion. So 100 million is like yesterday. There's still plenty of junk that can fall into Earth and kill us. So for me, that's the greatest existential threat. And what I worry about most is that 100 years ago, that wasn't even on the list. So I lose sleep. But what was on the list then? Well, you might die from tuberculosis,
Yeah.
or whatever. And I wonder what's going to be on the list 100 years from now that we don't even know is an existential threat.
But it
That's
won't
what
be artificial intelligence.
No, sure.
How could?
A fish, someone always just boom right there in your way, and it's usually someone big too, like Maui. Oh, there's Maui right there. I have some challenge I have to do with him, some quest with a kite, but I have to build another kite, but I don't have all of the materials I need to build the second or third kite, so I'm gonna have to figure that out too. Hi, Joanna. I have over 1,000 people chilling in my Twitch stream right now. Look over here. There's like 1,000 people.